We are from Group 4. We'll be explaining on Experiment 6, Bourdon Tube Pressure Gauge Open-Ended. So our group consists of myself, Mageswaran, Lim and Ki, Lee Wei An, and Manikandan. Right, today our presentation will be consist of a report summary, objective, apparatus, theory, methodology, result and discussion, conclusion, and reference. Alright, so I'll be briefly explaining on the report summary for this experiment, Bourdon Tube Pressure Gauge Open-Ended. So first we have to understand that instrument calibration is one of the primary process used to maintain instrument accuracy. So known weights have been applied on the dead weight calibrator to apply pressure to a fluid for checking the accuracy of reading from a pressure gauge. So one of these devices is a Bourdon tube pressure gauge, which is involved in our experiment today. So it was designed by the French engineer named Eugene Bourdon in the middle of 19th century. So it is based on a elastic spring, a C-shape, and a bent tube with an oval cross section. So how does this work? When the internal space of the Bourdon tube is pressurized, the cross section is thus altered toward a circular shape. And then the hoop stress that are created in this process increase the radius of the C-shaped tube. As a result, the end of the tube moves by around 2 or 3 millimeters, and then the deflection is a measure of the pressure. It is transferred to a movement which turns to a linear deflection into a rotatory movement and via a pointer. So it makes this visible on a scale. So with the C-shaped band Bourdon tubes, pressure up to 60 bar can be displayed. But for higher pressure, helical or spiral Bourdon tubes are used. Depending on the requirement, the pressure elements are made of the copper alloy, stainless steel, or special materials such as Monel. And Bourdon tubes are mostly used nowadays because of their reliability, compactness, low cost, and ease of use.
I'm Manika Nagasamy and explaining about objective and apparatus for experiment 6. Objective for the experiment 6 is to calibrate a Bourdon tube pressure gauge using a dead weight. Apparatus used for the experiment are Bourdon tube pressure gauge, piston and dead weight tester, as we could see in figure 1.
Hi, I'm Li Wei An, and now I will explain about the theory part. The Bourdon tube pressure gauge operates on the principle that when pressurized, a flattened tube tends to straighten or regain its circular form in cross-section. It is the instrument that used to measure the pressure by using the pressure sensing element for measuring the applied pressure. These pressure sensing elements deforms elastically under pressure. The Bourdon tube pressure gauge consists of a circular tube which is bent over an angle of generally 270 degrees and of which one end is closed and the other is connected to the process pressure. The closed end can move freely. This movement is transmitted through a transmission mechanism to the pointer of the pressure gauge. With the rate and pinion of the transmission mechanism, the movement of the Bourdon tube may be amplified so that the pointer rotates from start to end of the scale. The Bourdon tube behaves like a spring which is deformed by the internal pressure in the tube. The figure shown is the Bourdon tube pressure gauge. Next, we talk about the dead weight tester. The Bourdon tube pressure gauge is connected to a dead weight tester, which is basically a pressure producing and pressure measuring device. It is used to calibrate pressure gauge. The calibration of pressure gauge means introducing an accurately known sample of pressure to the gauge under test and then observing the response of the gauge in order to create an accurate known pressure. This tester is based on the principle of Pascal's law, which states that in a closed system of incompressible fluid, the pressure applied will extend equal amount of force in all the directions. The formula is pressure equal to force divided by area. Therefore, the pressure due to the added weight exerted on the piston with dead weight tester has fully transmitted through the transparent tube that reached the Bourdon tube pressure gauge. The reading indicated represents the pressure of the mass weight added. A piston of a known area is loaded by a known weight. Therefore, the theoretical pressure in the cylinder is equal to force divided by area of piston.
So, for the procedure, first we have to note down the cross-sectional area of the piston and the masses of the piston and dead weights. Next, we remove the piston from the cylinder first and pour the oil into the cylinder up to its overflow level. Then, we must ensure that the test gauge reading is 0 before inserting the piston. After that, we will place the piston into the cylinder carefully to reduce friction effects, and at the same time, we can tilting and gently tapping the transparent tube or rotating the piston softly to remove the air bubbles trapped inside the cylinder and tube. After set up the apparatus, we start to measure the pressure gauge in kilopascal when there is no weight on the piston and record the reading as the first pressure gauge reading after the system is stabilized. Then, we add a single dead weight which is 0.5 kg on the piston and record the reading of pressure gauge after the system is stabilized. We repeat the step 6 until total mass reaches 6 kg. Next, we remove a single dead weight from the piston and record the reading of pressure gauge for unloaded after the system is stabilized. This step is repeated until all the dead weights are removed. We will repeat step 3 until 9 for 2 times to get the average pressure gauge reading. After completing the experiment, we need to clean the apparatus and dry off the piston plug with a lint-free cloth. So, the specifications of the piston and dead weights are recorded below. The mass of the piston used is 1 kg and the cross-sectional area is 0.003173 meters squared. 10 dead weights will be used in this experiment and each dead weight is 0.5 kg. All the pressure gauge reading for the loading and unloading that we obtained from 3 repeated experiments will be recorded in this table 1 and the average values will be determined. Besides, the mass of the dead weight added as well as the total mass of piston and dead weight used in calibration also be recorded in this table. Then, the actual pressure, which also known as the pressure exerted by the total mass, and the percentage error for loading and unloading also calculated and recorded in this table. Discussion 1, we will going to discuss the deviation of percentage error. The percentage relative error is used to determine the accuracy of the experiment. The higher the percentage error, the lower the accuracy of the results. It is calculated by using the equation below, which is modulus of difference between measured pressure and theoretical pressure divided by the theoretical pressure and thus multiply with 100%. So the measured pressure is the gauge pressure obtained from the experiment and it is divided into loading and unloading, while the theoretical or actual pressure can be calculated using the equation force per unit area where the force is equal to the product of total mass and gravity constant. The percentage error calculated were recorded in table 1. Based on the results, the percentage error is significantly higher when there is no dead weight on the piston, which is 35.3%. This situation indicates that some problems with the piston inlet may happen in this experiment. For example, restricted motion or poor lubrication. Both of them may due to the oil use is in bad quality and not fully clean, which means that it may consist of some tiny impurities that will affect the movement of the piston, especially when the load is added. This is because the presence of impurities will block and restrict the movement of the piston and eventually increase the friction when the piston going down due to increasing of the weight. As a result, the percentage error for loading is relatively higher than unloading. And this can be proved by calculating the average of percentage error. The average percentage error for loading is 19.38%, while unloading is 9.85%. In short, the percentage error obtained is fluctuating, which means that the values rising and falling irregularly. This may be because of the surface or the gear system of the Bowden pressure gauge is damaged. Moreover, according to Nick Pick in 2018, The fractioning results could be caused by nonlinear elasticity of transparent tube, in which it has a varying constant of deflection throughout its top. Besides, other experimental errors may occur during the experiment.
Alright, so I'll be talking about discussion 2 for this experiment, which is the source of error and the method to minimize the error. So the first error is that the vibration has a negative impact on the gauge accuracy in two ways. Number one, it is difficult to read the pointer on dial when the gauge is vibrating. And number two, the incremental damage to the pointer mechanism from vibration can eventually move the pointer off zero. So eventually it will produce inaccurate readings. So how to solve this error is that we use a liquid filled case because it is the most convenient and the cost-effective way to protect the pressure gauge from vibration. And error number two is that the cardinal point or division markings on the dial face of Bourdon tube pressure gauge can be separated by a large amount, so it's making it difficult to read the pressure precisely. And the method to solve this error is that we should adjust the pressure calibrator so that the applied pressure is set to the cardinal point on the pressure gauge.
Then we proceed to discussion 3 to discuss about the repeatability and accuracy of this equipment. For repeatability for this equipment was displayed by the repeated times under same conditions, for example, the mass added for each time. This is to get average reading because the Bourdon tube pressure gauge can be regarded as a device that's sensitive to surrounding environment, especially the temperature fluctuations. From the experiment, the highest percentage error by comparing both experimental and actual results is 35.3%. This number indicates the experiment conducted might experience some inevitable errors or fluctuations. For accuracy of the equipment can be explained by the average reading that obtained by repeating the experiment for several times to get the most accurate reading among the repeated procedures. When the mass was added to the piston, the dead weight pressure gauge calibration response slowly result in the delaying that corresponding to the changes of pressure as well as the friction. To sum up, although the accuracy and quality of Bourdon tube pressure gauge has not reached 100%, by repeating the experiment for a few times to get an average reading, the result obtained will be more accurate and more reliable.
I'm Manika Nagasamy explaining about experiment 6 for conclusion. In conclusion, this experiment was carried out to calibrate a Bourdon tube pressure gauge using a dead weight. Throughout this experiment, the weight was loaded and unloaded by 5 kg until the final weight is 6 kg. The data of gauge pressure was taken for 3 consecutive attempts to minimize any possible errors. Since there is a minimal difference in gauge pressure, the percentage error was calculated to ensure the recorded data are almost accurate. The few possible reasons for this difference in reading, so the possible error and method to eliminate the errors were identified to ensure the accuracy of this experiment. Thank you.